Talk about Internet of Things, and you must have heard about Internet of Things now. I started talking about it when nobody had heard about it, so like 5 6 years ago. And so some of the first few slides, maybe like you probably don't need it, but in those days they needed it. So we'll talk about what is a thing, what are the business opportunities, what are the research challenges, what are the protocols, and some of the issues. And we are going to have 5 or 6 next lectures on IoT. First of all, Internet of Things. So what is a thing? Very simple definition. Thing is not a computer, basically. So thing is up until around 2010, this thing started, right? In 2010, all the computers were networked. And you couldn't have a computer which is not networked. But then people said, hey, now what we do, networking guys, right? So we said, okay, we could connect everything which is not a computer. Okay. So that is what Internet IoT is all about. You take out the computers, which is already taken care of, and everything else, which includes your chair, your table, your car, your shirt, your pant, everything else. Everything has to be networked. And so that includes, of course, we started with the phone, watches, thermostats, car, electric meters. Anything, anywhere, anytime, anyway, anyhow. So we should be able to get to everything. So right now, less than 1% of the thing around us is connected. Refrigerator, car, washing machine, etc. should be connected, but they are not. And many of these, the thing is, these becomes data, as I said, because now cars are connected. Many of the heaters and the air conditioners are connected. Garage doors are mostly connected, and so on. Okay. From 10 billion to $50 billion, this was a forecast that the market will grow, and 14 trillion in 10 years. Okay. So this was called Internet of Everything by Cisco and Smarter Planet by IBM. Okay. In fact, I remember writing a joke in 2009. We wrote a paper. And we wrote a paper about what's happening in networking and next generation internet. In that paper, we said, well, these guys in Europe are working on something called Internet of Things. And I don't know whether we wrote it or not, but basically we call it Internet of European Things because we are not interested. Okay, now we are all doing Internet of Things. Okay, so actually they were, in some sense, leader in this case, ahead of United States. So right now we have a smart grid, a smart health. That's a smart watch looks like, a smart home, smart cities, smart industries, smart TV, smart watch, smart car, and a smart wine. Okay, everything is smart because you can remotely control it. It is connected. Okay. So the question is, what is smart? So in old days, actually this slide has to be changed, but anyway, in old days, very old days, when I was growing up, people who could do computation very fast. If you could multiply 2063 by 2063 in a microsecond, you were very smart. Now I have to take some time, right? So your smartness was measured by your compute power. And then we grow up, basically the memory became the bottleneck. So anybody who could remember the first 100 digits of pi or all the capitals of all the world nations, they were very smart. Even today, a lot of people, they remember everything and they're called very smart, right? But then that changed too, because once Google came, you don't need to be remembering anything. You don't remember anything. You don't even remember your date of birth. You just Google it and you find it. So the smartest lies whether you're connected or not. Okay. So basically today, in this day and age, smartness is measured by connectivity. If you're connected, you're smart. Smart grid is smart because it is connected. Smart meter is smart because it is connected. Smart car is smart because it is connected, and so on and so forth. In fact, the student on the left is not smart because he is not connected, and he will take 3 days to find the answer. Ask him something, and then he will take 3 days. Guy on the right is smart because he's connected. here's the Wi-Fi connection. You ask him what is it, and he will just find out from Google. So the thing is, and that's what students do. I mean, this is smart class, but in the last class I've seen that most of the students, wiggling on their smartphone, and you ask the questions and they know the answer right away. So smart actually, so that is the definition of smartness today. However, this slide is now 7 years old. I wrote this slide myself 7 years ago. Now I realize this year, 2018, that this slide is getting out of date. Today, the smartness definition has changed. Really, smart means using the latest technology. So latest technology now become AI or something. If you don't use AI, you're not smart. So that is what it is. Smartness definition is slowly changing. Right now, it is still connected. All of those things I told you that are smart, but now many of the smart cities are saying, well, that is not enough. We want to use the latest technology. Okay, so that definition is applied all the time, even when I was young and when I'm old, and even after me. Smart means using the latest technology to solve the problem. So the question is why we did IoT now and not 10 years ago or 20 years ago? Well, 20 years ago, things were not right because IoT requires sensing, IoT requires communication, and IoT requires computation. And now the sensing has become very cheap. For $5, you can buy 20 sensors nowadays. So sensors are few cents a piece. Communication has become very fast, actually, and very cheap as well. So now you can have a very small chip able to do Wi-Fi, and it will again cost few cents. Computation has become very cheap because the computers, the chips are very again. So micro sensors, micro server, micro computing, cloud computing, all of these things have made IoT possible. In fact, I should mention this one is the RFID and the QR codes. They also made it possible because RFIDs can work without power, right? You know what is an RFID? Okay, when you go to the store and you buy something, it has a magnetic thing attached to it. If you take it out of the store, it will buzz. That is RFID, radio frequency identifier. So everything that is in the store now has an RFID in it, and if you take it to something, it will communicate and tell them that, okay, this guy is taking out. When you buy it, if you buy it, they put it on the magnet and it demagnetized it, and then you can take it out. Right? So RFID doesn't even need a battery. And the QR code is same thing, QR code, which I show at the end of every lecture, that you can communicate, you can get right away, you can scan it, and you can get from the internet the lecture. So energy efficient communications, small or no batteries. Previously, the communication required lots of batteries. And I mean, let me give an example. So when I started recording my lectures about 15 years ago, 95, 23 years ago, half of this room was the list of computers. We had 3 big desktops and monitors, and a guy sitting there, managing all the monitors to record everything. Okay. Today you don't even notice it because it's all there. Okay. We had a special microphone, a special everything, a special internet to broadcast to the internet. We did this in 96, 97 time frame. Now, everything is, computers have become small, the communication has become small, and everything is, much better. Microcomputing, microcore chip, Raspberry Pi, Intel, Galileo, Arduino. You can buy Raspberry Pi for $20. It's a full computer. Cloud computing means you don't even have to do computing. You can just give it to the cloud. And the operating systems have become free, Linux. So all of these things were not possible. Now these things made IoT possible. So if you look at the Gartner Hype Cycle in 2015, you will find that IoT was right there on the top of the hype. All right. If you go in 2018, it has come down. So basically now it is becoming everyday affair. Okay. I mean, now we have a lot of IoT. And basically now there are still some things to be done on the left side. And they have for IoT, they have a hype cycle. And so this tells you in IoT what are the problems on the left that people need to solve. And so right now the problems are real-time analytics, again AI, embedded software security. Security is an issue. IoT platform is an issue. So those things, right? And these things are coming down. Home is coming down, big data is coming down, and so on. If you look at Google Trends, then you will notice that in 2009 we made a joke of Internet of European Things. We didn't have, nobody was worrying about Internet of Things, right? Suddenly in 2014 January, Google bought Nest for $3 billion. Now Nest is a simple thermostat company. $3 billion. Honeywell has been making thermostat for 100 years, and they are not worth that much, right? What is the difference about Nest? Nest is IoT. And suddenly everybody is looking for IoT, and so suddenly the Google search goes up through the roof. And why it is going through the roof? Because if you are in computing or if you are in communication, if you stay in computing alone, you are not going anywhere, right? If you get into IoT, there is a lot more demand. Okay, so all the networking companies, they are getting into IoT. And here is another interesting thing is that IDC, which is a company which forecasts the future for the businesses, they said 1.7 trillion by 2020. Trillion in IoT. Now Gartner says, no, it's too low, 7.1 trillion. And then GE says, oh, that is too low, 10 trillion. And Cisco says, no, that is too low, 19 trillion. Now these are all guesses, but everybody is just kind of hyping, super hyping. All this shows is there is a big hype about IoT. So here is a 7-layer model for IoT. We are like 7-layer models. 7-layer models of networking, right? Here is a 7-layer model of IoT. And this is not the 7-layer model that we talk about for networking, but these are basically 7 layers to make IoT possible. First of all, you need to select a market, such as smart grid, connected home, smart health, smart cities. Once you have that thing, then you have to decide what sensors you need, cameras, GPS, meters, phones, whatever. Once you have them, then you decide how to connect them. So you need to worry about the data link, Wi-Fi, Bluetooth, Zigbee, NFC. Once you have connected that, then you have to collect the data, and then you have to combine the data from other sources such as GIS, Geographical Information Systems, population data, economic data. All of the data is connected with sensor data. Then you have to do analytics. Then you have to do machine learning on them, predictive analytics, data mining to make some sense out of them, right? And then you have to do application level stuff such as software defined networking, software oriented architecture, cloud computing. And once you do all that, then you get a smart energy, smart entertainment, smart health, smart education, smart transportation, all of these things, right? So now you can notice that out of these 7 layers, the middle 5 are what we call ICT, information communication technology. Information and communication technology. So if you're a computer scientist or networking guy, you can do this bottom, these middle things, right? And that's what we are. We are ICT people. So we do these middle things. And don't forget that all of these things need security and management as well. So this shows you what are the research issues. The research issues on every layer. So if you are working on the top layer, you will worry about SDN, SOA, cloud computing. If you're working on the bottom layer, you will worry about sensors, cameras, how to make them and all that, right? So in the 5 layer, you have to design how to design smart devices. At the data link layer, what we are going to do in this lecture, in this class, is Wi-Fi, Bluetooth, Zigbee. We will talk about all these protocols. Routing layer, we will talk about how to route among all these. analytics, people are working on big data, data mining, machine learning, and so on. So there are plenty of issues to be solved in this case. Okay, and those issues become very clear when you look at this 7-layer model. Otherwise, you might be working on cloud computing but not realize that you can use it for IoT. You might be doing machine learning but not realize that you're using it for IoT. So all of these are IoT related. Here is a cartoon. Now, one thing about IoT is that Google knows everything. So they know exactly what time I came to office today. They know exactly what time I left yesterday. I don't remember what time I left, but Google knows because I'm connected. My phone tells them. My home tells them. In fact, once I was driving on the road and it says the roads are clear, you will reach home at 15 minutes. I said, I didn't ask. This information was pushed to me because it knows that I'm going to home, And so this guy has a joke here. I think my Nest smoke alarm is going off. Google just pitched me a fire extinguisher. And this is true, actually. The thing is, when you search any web page, you will find the advertisement about the things that you had searched before. So, so they tell you exactly the things that you're looking for and are what you need. Okay. So in my home, basically everything is now connected. All the alarms are connected. The cameras are connected. If anything happens, they know exactly what time water alarm went off, things like that. Anyway, so now if you're a businessman, then there are opportunities here. Again, going back to the layers, you can design new sensors, you can design new microprocessors, you can implement new data links, systems, analytics, and applications. Now, it turns out the money is in this direction. The higher you are, the more money there is. Okay, so there is a lot more money you can make with applications and with analytics than systems and data links and microprocessors and sensors. Sensors, people don't make much money. Only if you put the application, then you make a lot more money. Okay, so the Nest alarm, by the way, Nest smoke alarm cost $200. Okay, but that is not for the sensor. That is the application, right? That sensor, there is smoke alarm sensor inside it, which probably costs less than $1 because every smoke alarm has that sensor, and they cost only $10, right? So the sensor cannot be very expensive. Microprocessors cannot be very expensive, but these things are all very expensive. All right. So if you are working on if you're thinking of working on something, try on the top layer. Well, I mean, these products are now, I don't have to give examples, but there's a Vimo, which we have in our lab actually, and we use it. I mean, we don't use it, but you can turn on anything with a phone. This is a wireless cardiac monitor. This is a Nest thermostat. This is a home automation, probably some kind of a vacuum cleaner. You can do it remotely. There are processors, there are chips, there are platforms. Okay, so if they all join software framework, just like Linux is a open source operating system, Alljoyn is a source software. So if you ever want to do anything in IoT, you want to look at this Alljoyn framework and these development platforms and so on. So anyway, so much about IoT. All right, introduction. What else is happening? And so one thing which is happening because of IoT is data is moving to the edge. What that means is that previously you used to go to this central computer, maybe Amazon, to do anything, right? Cloud. But now the clouds are everywhere. They could be, so basically the carriers are going to put the clouds on near every tower. Actually, they're right now putting into offices, into every carrier office, but soon it will come to the tower. So basically, when your phone or your device reaches a cloud, it doesn't have to go all the way to California. It can get it right here. So for example, when you tell Siri, okay, please tell me what is the directions to my home, that analog voice has to be digitized, right? And then it has to be looked up into Google database or whatever, right? All that is done somewhere else, very far away. And if you have some other country, it will take long time for that to come back, the answer to come back. So basically, good would be that if we can do the digitization and everything right here locally, then the answer will be very fast. So that is what is happening, and this is called edge computing. Okay, computation in the edge, basically. So it's not just the cloud includes we call them micro clouds. So the micro clouds, they're not like a data center, they are just a small computer which can have many processes. So this is called edge computing. And then it is called fog computing, because if you have computing everywhere, if you have clouds everywhere, then that is called fog. Right? Have you seen fog? Right? Fog means it just steam everywhere, right? And so that's what is happening now, right? And we call it multi-cloud. Multi-cloud means your application will run not on one cloud, but on this cloud, that cloud, as well as on the big clouds at the same time. And we did all this research in 2009, 10 time frame on multi-cloud. Now it is all common. But anyway, we developed as one of the PhD thesis in our group. We developed so this we developed this platform. This is in our lab, and this platform is called Multi-Cloud Application Development, MCAD. Okay, Multi-Cloud Application Delivery, MCAD. And this platform has two things. It has interfaces. So first of all, the people who are developing the application can talk to it in their own way. Then there are architects. Now, architects are not developing the application. So let's say you are writing an application for thermostat. There is a guy who is writing thermostat application is right here. Then there are architects who are worrying about the security of that thermostat, security of the information. So they want to put some firewalls and certificates and things like that. So they talk to our system. And there are people who are deploying the application. So for example, if you have a factory, or if you have a big enterprise and you have lots of thermostat, then you have your own application, your own requirement that use this cloud, use that cloud, whatever. So those are, you can talk to us. Our platform then can talk to many clouds. It can talk to clouds using OpenStack. It can talk to clouds using EC2, which is Amazon's thing. It can talk to networks using Open Daylight. So we have written drivers for each of these. Okay. So our system can talk to any of these clouds. And so now this system can be used by anybody without having to redevelop it. Now this we did in 2010, but now this is very common, and there are many private softwares and open source software which do this multi-cloud. Here's an example of multi-cloud application. Here, basically, let's say you are wearing a smartwatch or a health belt, and suddenly your blood pressure goes up. Then the watch, the monitor tells the phone, and the phone tells the tower that the blood pressure has gone up. And so there is a cloud on the tower which analyzes the situation and says this is too much, and we got to tell the doctor. The doctor is on another cloud, right? And then the doctor says, yeah, this is very important. The guy has to be going to the hospital. So the hospital cloud is informed. The insurance company cloud is informed. Now these are all different clouds because you cannot do all of this in one cloud, right? Each one is owned by a different company. So that's where you need our platform. If you had our platform, then only one person, this application developer, can deploy it and put all the rules together as to which hospital for which person and which doctor for which person. All of that can be done using this MCAD. Okay. And so this is a multi-cloud. This is what is happening because of the IoT. Any questions about this? So IoT was done before, and these are all the protocols. I will not go in through them. But BACnet, LANWorks, Modbus, KNX, G-Wave. So these are used in the factories mostly. If there are things connected in the factory to each other, they use these protocols. And now we are developing some new ones. So those are the ones that we'll talk about. These are legacy, means old. So the recent protocols are these. Okay, and there are tons of them. I don't know whether I can even read all of them. But what we will do is we will discuss the ones which are in red. We will discuss Bluetooth, 11AH, Zigbee, and LoRaWAN. Okay. And then there are lots of them here for security and management. Every standard body is working on IoT. So nobody wants to be left behind. 11 is working on it, 15 is working on it, HomePlug is working, Zigbee Alliance, Bluetooth Alliance, IETF, ITU, ITSI, IPSO, 3GPP. If you're not working on IoT, you're not a standard organization. IoT is hot, right? So everybody is working on it. And 7 organizations joined together. So Arab, ATIS, CCSA, ETSI, TIA, TTA, they join and they call it one M2M. So sometimes you'll see a standard called one machine to machine. And so they means, these, instead of doing it separately, they just did once. And so there's a whole set of standards. The main issue in data link is energy efficiency, because energy of the previous protocol was very high. They required a lot of power. And now it is going down by a factor of 2 every year. And you wait 10 years and the power will be very little, or you do some better protocols. We are doing better protocols. The IoT messages are very small. In the computers, when we used to have before, the message used to be very long, right? But with IoT, all they are going to say is the temperature is 13 degree. So it's not much, right? So the messages are very small and limited computing. Because they cannot compute, we need lightweight protocols. They cannot, so the quality of information, and basically the information itself may have a different quality. If I told you the temperatures once, I can tell you 15 times, it's not really important, right? So that's a different one. Now, so the way we measure the power is how many kilowatts per megabyte. So Aero 2.11b required 36.4 millijoules per megabyte. This is the energy unit. How you calculate that? Because it gives you 11 megabits and the transmitter sends 50 milliwatt. So using these two numbers, you can calculate how many joules per megabyte. And G was less, A was more, 15 is less, and 15.2. This is the one that was designed. These two are designed for IoT, but this one is not good enough. This one is 0.03. So this is where we are getting to, is you really want to get microwatts and microjoules. Second issue is that the numbers are large. Previously, the computers were a small number. Like in the university, might have 5,000 computers. But in terms of devices, we might have 5 million devices. Okay, the world population is 7 billion, right? So the computers might be 7 billion, but the devices could be 100 times that, right? So 32-bit addresses cannot work. So 48-bit addresses cannot work. So 128-bit addresses will work, but they are too large. The devices cannot handle that. So now they are working on 64-bit addresses. We will see how the 64-bit addresses work. And so those are 64-bit global addresses and 16-bit local addresses. So what happens is when you have a small network for IoT, we just give you a local short name. so that we don't have to send you 64-bit every time. So that is 16-bit, but your unique global name is 64-bit. And so there are protocols called 6LoWPAN or 6to9 IP. These protocols, are designed especially for personal area networks for IoT. And so basically last 100-meter protocol is, so now we have basically a gateway which comes to home. From gateway to phone is 100 meters. From phone to device is 10 meters. So we are developing these small protocols for the last 10 meters and last 100 meters, right? And we will discuss them. So this is basically Bluetooth, this is Wi-Fi, and so on and so forth, right? So we'll discuss those protocols. So anyway, the summary end of IoT is that less than 1% of things are connected. Okay, and therefore IoT is a big opportunity for academics and industry. Smart grid and energy management is leading the change. In the United States, basically in 2009, smart grid started. The government put lots of money on that, research money. So we all started working on that. And so that is leading, and then slowly we are getting into this. Smartness comes from communication capability. So right now, communication makes you smart. And we are right at the knee. Knee is basically that hype chart, right? Where academic and startup research opportunities in almost sub fields. So basically, there are so many opportunities. Remember that 7-layer diagram. Any layer you are working on, you can do research or development. And cloud computing is getting everywhere. So that is what basically, because of the IoT, there is cloud computing. So anyway, so this is just an overview of IoT. What we will do next is we will discuss protocols, some of the protocols that we mentioned for the next 3-4 lectures. So